Okay.
Cool. So I'm going to be talking a little bit about exponential change and how it relates to animal populations and stuff. So exponential change, sorry, I have to move the, still see everybody's faces. Okay, cool. So exponential functions increase or decrease very rapidly with changes in the independent variable. These changes describe growth or decay in many natural or industrial situations. These are said to undergo exponential change. Some examples would be size of population, which is kind of what I'm going to be focusing on. Other things would be like the amount of decaying radioactive material or a temperature difference between a hot object and its surrounding medium. You have the law of exponential change, which is y equals y naught e raised to the power of k times t. And when you're looking at growth, with this, k will be bigger than 0, and then decay would be k less than 0. And k is the constant rate of the equation. I have two graphs here. This graph represents the exponential growth, and then the graph on the right is the exponential decay. Cool. So now to get into how we get that equation, you have dp divided by dt equals kp. So you just divide, or you multiply each side by dt to get dp by itself. And then to get p by itself, you divide by p, and you get 1 over p equals k dt. And then you have to sorry, I don't.
You integrate?
My screen froze, sorry. Cool. All right. So we have to integrate both sides of the equation. So to find the antiderivative of 1 over p would be the natural log of p, and then k is a constant, and then the antiderivative of dt is t, and then you have to put in the general constant c. And then you can put the equation as an exponent of e, and when you do that, e and ln cancels out, so you get p by itself, and then you have e raised to the power of kt plus c, which you can separate that side and make it just e raised to the power of kt and times e raised to the power of c. And because c is a constant, you can just plug that in as c by itself. So you have the equation pt equals c times e raised to the power of kt. So then we'll set the equation to 0 where t is. And when that happens, you have p0, that says minus. Cool. So whenever you have anything raised to the power of 0, it becomes 1. So you have p0 equals c, and that shows you that c is the initial population. So you could just put the current population pt equals the initial population po times e times kt, which is the growth rate and time. And this an example over that. It's one I pulled from the book. So biologists consider a species of animal or plant to be endangered if it is expected to become extinct within 20 years. If a certain species of wildlife is counted to have 1,147 members at the present time, and the population is steadily declining at an exponential exponentially at an annual rate averaging 39% over the past 7 years, do you think this species is endangered? So you can use this equation that we just derived. You can plug in the initial population, which is 1,147, and then the growth rate, which is, because it's declining, it's negative, is 39%. And then the time is 20 years. And once you plug all that into your fancy calculators and stuff, you get 0.45. And because since the population at 20 years is less than 1, the species is endangered. And I pretty much just used the book for it. So